Hello everyone, my name is Madhulika Ankam and my teammate name is Anusha Challa, and the topic of our paper is UniControl, a unified diffusion model for controllable visual generation in the wild. So the background of this work is the boom of AIGC. The term AIGC refers to artificial intelligence generated content, which encompasses any content generated through the use of artificial intelligence technologies. This can include text, images, music, videos, and other forms of media. AIGC leverages machine learning models and algorithms to produce content that can mimic human creativity and intelligence, often requiring minimal human intervention. The technologies behind AIGC include natural language processing, computer vision, deep learning, and generative adversarial networks. AIGC applications are diverse, ranging from generating realistic images and artworks to composing music, writing stories, producing synthetic voices, and even creating virtual environments. AIGCs have progressed a lot due to the increased availability of massive databases and achievements in human computing performance. We all know that in 2022, OpenAI has released a new chat robot model called ChatGPT. It is capable of understanding human language and generating text like humans do. About 13 million independent visitors were using ChatGPT per day in January 2023. With the improvements of products like ChatGPT, AIGC has shown great potential for applications and commercial value. It has attracted a lot of attention from various domains, including entrepreneurs, investors, and the public. As in technologies, as technologies evolved, AIGC is becoming increasingly sophisticated, enabling more creative and complex content generation. At present, the quality of AIGC content is significantly better than it was in 2022. We have seen a lot of AIGC work like the DALI, latent diffusion, ImageNet, stable diffusion, ControlNet, which have achieved very good results and also have a high impact on the community. Related works. So first is the diffusion-based generative model. This model has evolved to effectively generate high-quality images. Initially introduced for image generation, these models have seen improvements through score-based diffusion, denoising diffusion probabilistic models, and denoising diffusion implicit models, which enhancing image quality and generation speed. To accommodate high-resolution imagery, researchers have developed techniques like using image pyramids, multiple processing stages, and latent representations to expedite the generation processes. So here in the diagram, if you see, this is a diagram of diffusion denoising diffusion probabilistic models, which we call DDPM. DDPMs are a type of diffusion models used for probabilistic data generation. As mentioned earlier, diffusion models generate data by applying a sequence of transformations to random noise. DDPMs in particular operate by stimulating a diffusion process that transforms noisy data into clean data samples. To train DDPMs, the process entails acquiring data of the diffusion processes parameters, effectively capturing the relationship between clean and noisy data during each transformation step. During inference, that is, when it comes backward, DDPM start with noisy data, like noisy images, and iteratively apply the learned transformations in reverse to obtain denoised and realistic data samples. DDPMs are particularly effective for image denoising tasks. They can effectively remove noise from corrupted images and produce visually appealing denoised versions. Moreover, DDPMs can also be used for image in painting and super resolution among other applications. And the second related work is the text to image diffusion model. This model have achieved top tier performance. These models integrate advanced techniques such as combining unit denoisers with textual embeddings from clip to understand and convert text description into corresponding images. Glide is noted as a prime example for such a model, which not only generates images from text but also allows for image editing. Here, if in the image, if you can see, we are giving the input as a hedgehog using a calculator, and the image produced is a hedgehog on using a calculator. It is pretty accurate, as you can see. And the third related work is image to image translation. This model was initially pioneered by Pix2Pix, which aimed to transform images across different domains through learning mappings. The field has seen a significant advancement with diffusion based methods setting new benchmarks for image translation and editing, demonstrating superior performance even without paid training data. Techniques like prompt to prompt and edit show the progress in diffusion-based image editing, offering solutions for tasks such as colorization, super resolution, and in-painting through innovative approaches such as diffusion bridges, flows, and classifier-guided methods. So we will learn about ControlNet. ControlNet is a sophisticated framework designed to enhance the capabilities of pre-trained diffusion models like stable diffusion by adding a layer of conditional control. It achieves this through a unique architecture that separates the model into two distinct components: a stable, unchangeable fixed copy of the original diffusion model, and a trainable copy which can be fine-tuned based on specific requirements or conditions. This dual structure design allows for the integration of spatial visual conditions such as layouts, skeletons, and edges into the image generation process, enabling the creation of images that align closely with these input conditions. If the fixed copy serves as core foundation, maintaining the original model's parameters unchanged. This ensures that the model's inherent capabilities and knowledge derived from extensive pre-training are preserved. The trainable copy, on the other hand, is initialized with the same parameters as the stable diffusion model, but is designed to be adaptable. As the model is exposed to new data or condition, these parameters can be updated, allowing the model to learn and incorporate additional information beyond its original training. To effectively combine the outputs of the fixed copy and the trainable copy, ControlNet employs a novel approach using zero convolution layers. These layers act as a bridge, initially neutralizing their impact on the model output by setting their weights to zero. However, as the trainable copy is fine-tuned, these zero convolution layers can be adjusted to modulate the influence of the input conditions on the final image generation, enabling a seamless generation of the fixed and trainable components. This structure allows ControlNet to leverage the strengths of the stable diffusion model while introducing a new level of flexibility and control. By adjusting the trainable copy based on specific visual condition, ControlNet can generate images that not only benefit from the high quality output of the diffusion model, but also closely match the desired condition, offering a powerful tool for customized image generation. Um, But the key limitation of controllers lies in its inability to perform multitasking, meaning it can't handle multiple tasks simultaneously within a single model instance. To tackle different types of visual condition like generating image based on the canny edge images, or focusing on image segmentation or any other specific task, it needs a separate model. This limitation requires dedicated training and optimization for each unique condition or task you want to model to perform. For instance, if you want to generate images that follow the layout provided by canny edge detection, so the first image is the canny edge image. For this, you need a separate model, and if you give a scribble input, you need a separate model. And also for segmentation, we need a separate model. So this is the basic key limitation of the ControlNet. And this approach contrasts with more versatile models that can handle multiple tasks simultaneously without needing separate training for each condition. The requirement of separate models for each task could lead to increased computational and time resources needed to achieve desired results across different conditions. It also means managing multiple models for different tasks, which can complicate the deployment and application of such a system in broader, more varied use cases where flexibility and multitasking capabilities are essential. The limitation of requiring multiple models for different tasks in controller leads to a scenario where you end up with numerous checkpoints for each task. This situation not only demands significant computational resources but also results in lower efficiency due to the need to manage and operate multiple models simultaneously for different tasks. So, to overcome this challenge, inspiration was drawn from a concept known as visual taxonomy to build this paper, in which various visual tasks share underlying similarities, particularly in their geometric properties. For example, the canny edge, the segmentation, and the depth images, all three should have something in common in geometry, which could be learned together and would be beneficial for each other. These tasks, despite appearing distinct, can benefit from learning shared representations that capture these underlying geometric similarities. By leveraging the shared similarities across tasks, a model can be designed to learn a more generalized representation that supports multiple tasks simultaneously. This approach not only improves computational efficiency by reducing the number of necessary models and checkpoints, but also enhances the model's ability to generalize across different visual conditions. It suggests that learning from one task can positively influence performance on another by exploiting the commonalities in their geometric or structural aspects. In essence, this strategy aims to create a more integrated and efficient model approach that can handle a variety of visual tasks without the need for separate models for each task, thereby addressing the limitation of the original control net's design.
The motivation behind having this unique control model over the control net is that each input condition would have a individual model that will have an output result. This is getting a complex, and it's good to have an altogether conditional task handled by one model. So this comes with an idea of control over control. It's like each model that is a control net, it has a controller which is stable diffusion, and applied another controller called hypernet, which is to control the control net. So this is kind of an inspiration that held up for the hypernet, which inputs the feature and generates the parameter of the model, and then its parameter is specifically adapted to different tasks, and also inspired by the style jet, and to have a style features multiplied to the weight of the backbone that is adapted for the different styles. So in this methodology, the main concentration is on the hypernet, and then there is a weight modulation. So this comes up with an idea of UniControl. So before going through this entire reason and what are the modules that are involved in the UniControl, I wanted to walk you through this UniControl demo. So this is an API that supports what all tasks the UniControl model can handle. So initially it starts with Kenny, which is a control task, and then it is an HAD, and then it is sketch, then it is depth and normal human pose segmentation, and B-box, outpainting, in-painting, colorization, and deblurring. So each task in here, it has a certain inputs that user has to give. One is an image and next is a prompt. So this simulation will have an advanced options that will give an image, which is like how many images the model has to generate, an image resolution, control strength, and this is a condition. Let's say that you're inputting an RGB image that will convert to Kenny. It will happen otherwise as well. So let me start with Kenny here. So let me upload one sample image that I have taken from the paper related data samples. So I'm taking it from data. It has an individual folder for each condition task. So I'm going to Kene, and this is named as Kene. So it's like the Kene edge is like familiar image that everyone must have been having a pre-knowledge about it. So here I'm giving a prompt, which is like breadth of the wild compressed cover art. So let me go back and correct this compressed. Yeah. So since it is not an RGB image, I have to just disable this condition and go back to this and then click on run. So here the actual model would run by taking up this edge map, edge map, and it will give a resolution image, which is an actual image, and this is an what the high resolution image. So next I'm switching to HED. So here I'm uploading a HED image. So it is in the same data folder, then HED. Then I'm giving a cake image here. So I'm like fond of the chocolate here. So I'm just clicking is like the chocolate cake. So since here it's not an RGB, again I'm disabling this condition. So I'm going back and then I'm just clicking on run. So this would have the original HED map image and then the converted colored image. So here you can see the ME cake here. So the next one is a sketch. So I'm going back to the different folder here. So which is the test images. I'm selecting the image which I just selected random. So I can figure it out, it's turtle. So I'm just going to give a simple prompt which is turtle. And then I'm coming to the options. It's not enabled here. So by default, it's not enabled. So it's like I'm just clicking on run. So this will give the actual colored image of turtle, which is like a model has processed it and it's going to give a final output, which is this. And next it is depth map. I guess depth map is something like everyone are sure of getting the knowledge about it. So I'm going back to the data folder and then it is depth folder. So here it would have a name of 72. I'm just taking this random image, which is 7257. So we can figure it out. There is one animal and this one bird. So based on this, I'm just giving a prompt, which is a polar bear. So I'm just correcting this. Walks towards. I'm just figuring out it's thirsty and it's going towards the water. Then it's just I'm just connecting this first sentence to the second one, saying while a large bird lands on the opposite bank. So it's kind of I'm giving whatever I'm picturing out from the input I'm giving here. So I'm just disabling this since it's not an RGB image here. So I'm just running here. So this would take up this prompt as an input and it would give it this image where it's kind of polar bear actually coming for the water. So next category is of normal conditional task. So I'm taking up a different image here that falls under normal, which is in data normal. Yeah. So I'm taking up 25062. So we can figure it out. It's a teddy bear and there's something behind. So I'm hoping those are some kind of DVDs or some books or something. So what I'm doing here is I'm just giving a prompt saying that it's a line of small teddy bears are in front of several DVD cases. Okay. So since it is not an RGB again, I'm just disabling this. So I'm just clicking on run. So based on this image, I'm just giving a prompt which makes sense. So it's gonna take up this image and it's gonna give like beautiful picture of teddy bears here. And next comes a human pose. It's just kind of a skeleton that I'm giving and I'm giving a prompt to it. So here I'm going back again to the images that paper has provided. It's data and then human. It's gonna be in segmentation open pose. Yeah, it's gonna be in open pose. Yes. So here it's like 165. So based on this, I can figure out like some one is actually standing. So I'm just giving a saying of prompt like photo of handsome man in black leather jacket. So again, going back to the advanced options, it's not an RGB, so I'm just deselecting it. So I'm just clicking on run. So here it's gonna just figure it out based on the prompt and the image we have given here and condition. It's gonna give it this image. So the next thing would be like segmentation. So I'm going to give the segmentation image here, which is in seg base. I'm clicking on open and I'm selecting this 66141 image. So based on this, I can figure out we have like, it's a kind of hall area and with few furnitures here. So I'm going to give a prompt like it's a well lit and well decorated living room, shows a glimpse of a glass window through the corridor. So it's kind of, I'm just giving it here. And again, it's not an RGB image, so I'm just disabling it. Then I'm running it. So based on this segmentation maps that we have given and the condition task we're giving, it's gonna give this image. And then it is a B box, which is a bonding box here. So I'm selecting one image here. It falls under data, B box, and B box. So I'm just giving a random text here. It's like a man with glasses and wearing a tie, poses for a profile picture. It's just a random text I'm giving here. So, and similarly, going back here and I'm deselecting it. So this would generate a clear image of how this VBox has been converted to this. So on the next is the outpainting. Outpainting is something like it'll have something on top of an image. So I'm just think of a patch that is present on top of an image. So I'm going back to outpainting here. It's kind of enlarging, I can be in specific. So I'm just opening this. It's kind of, we just have to outpaint it. So it's a patch version of the main thing. So it's like Melbourne by Descartes. So it's kind of, we're just providing that within our advanced options. So by default, it's not enabled. So we're good to go. So I'm just clicking this. So this will have an enlarged image of the actual painted image. So this is an actual one. So the next is in painting, conditional task. And here I'm going back to data. It's in painting folder and then it is control 9. So it's like here you can see a clear image, but there is something part of it is covered. So with this prompt, I'm just going to tell the model to just take out that it's kind of you can visibly see that the sunset screen and it's in valley. So I'm just going just attach this all variables and words. I'm just linking to a prompt. So just the run here. So it's just gonna give a complete image that depicts the entire prompt here. So the next thing is a colorization. So here I'm gonna select a image that is not actually colored. It's a black and white image. So I'm just going to give this as an colorization, which is data and which comes under outpainting is done, open face and grayscale. So yeah, here it goes. So I'm giving it as an control 6. Yeah. So I'm giving a prompt as gray wall of chain. So I'm just running it. This would give a colored image of wall of chain. So in this way, it's kind of giving a clear picture of it. And then it is deblurring condition task. So here it comes with a different folder, which is a deblur. Yeah. So I'm giving a control 2 as an image. So here it's kind of a river flow. I'm just giving a related prompt here. It's river flow in mountains. Yeah, just running it. So this has this is going to give a cleared image of the prompt which you are going to try. It's kind of a clear image here. So going back to the slides, so we have seen this entire thing of how the actual UniControl has in terms of the how it's gonna process the image that the user has given and how it's gonna take up the control task and how the output is generated. The main key point here would be like it should satisfy the two properties here. The first thing is it should overcome the misalignment of low level features from different tasks. So it's kind of that should learn necessary and unique information from all tasks. So the task is like whatever the category I just showed you, with each image that I uploaded and each output it has given it up. So let's say that I have taken up a UniControl model demo and I've showed you a segmentation map. So that has a certain visual condition that I have given, and the model might ignore a 3D information in that. But ultimately, it learns a future map that may not be suitable for the task, and that might be suitable for the depth map as well. The next property is that it learns a meta knowledge across tasks and adapt to each task effectively. It's like it's gonna share the knowledge across tasks as well as the differences among them. So this is an architecture that has an inside the control net, and then we have a two major modules here, which I can say the task aware hypernet and the MOE adapter and the modulated zero convolution layer. So here the unit control which inputs the task and then it views the conditions and the text prompts and it takes the task instructions like the can edge image generation or the depth map generation, which will be input to the task hypernet here. And then it has a clip which is the encoder, and that clip will include the prompt as an embedding and then have some base hypernet and then the linear layer to project the final task embedding here. This is the final task embedding. So this is gonna be back to the main module, and this final task embedding will be applied to modulate this modulated zero convolution layer. And then this way that it gonna be applied for the different task here. And then therefore, this is kind of enhancing the adaptability to different tasks of this background. And also we have this MOE adapter, which is kind of, it's better in terms of adapting to different visual conditions. So the MOE model or MOE style adapter that is part of an entire UniControl module is something like it comes up with this equation that it has an indicator function and then it has a condition image for task K, and then it has a convolution layer that is f of conv1 and f of conv2. These are the convolution layers that has an ith module of the adapter. So when you see this image, this has something that to deal with most of the MOE hybrid task generalization. So the hybrid task generalization is something we just saw a demo that talks more about this hybrid. It's kind of when you see this image, which is the left side, we have a two different visual conditions as input, which has a segmentation map, which is this one, and then the human skeleton. So based on this, we are giving a background and foreground information. So out of this, we again have to give a hybrid task, which is a segmentation map and human skeleton to image. So this goes under the MOE style adapter in the entire UniControl model, and that gives an output of the image that the user is expected. And next comes a zero shot new task generalization. This has something like the actual model is not trained for that, but even then, it generates the controllable image on a newly unseen visual condition. So in order to achieve this, it estimates the task weights based on the relation between the unseen and seen pre-trained task is essential. So then it comes the task of how the each task weights are assigned. So these are assigned with manual assignment. It can be calculated the similarity score of task instruction in the embedding space. So this has a more details of the hypernet here. So hypernet task aware module is something, it has the task instruction into the task embedding with the help of a clip text encoder. We just saw in architecture, it has a clip text encoder here. So and next it is similar to style modulation in the style gen 2, which is injecting this task embedding into the trainable copy of control net by multiplying the task embedding to the each zero convolution layer. This is evidently seen in the architecture of the control net model, and it can be seen in the UniControl model as well. In specific, the length of the embedding is same as the number of the input channel of the zero convolution layer, and each element scalar in the embedding is multiplied to the convolution kernel per input channel. So this covers the major modules that are in the UniControl module, which is a MOE style adapter and next to the task aware hypernet. So here comes the comparison of UniControl with the control net. So this comparison is something it talks mostly about that each module and each model has similarity in terms of parameters, but one has to just think about how far these two models are capable, and it has this huge ability. So maybe in the future one can think about how far these models can be increased in terms of ability, not in terms of size. So here, if you can see, this entire picture depicts that it has a pre-trained task which we just saw in demo, and each falls under this pre-trained task. I just said about zero shot task as well. It's kind of image colorization, deblurring, and in painting as well. So next comes some details about how this paper has covered the experiments. So it has conducted a series of comprehensive experiments across various conditions and tasks. This has utilized a wise data set, and it has challenged the model adaptability and versatility. So this entire paper has a data collection that has started from the scratch, which is called as a multi-gen 20M. So this data collection majorly involves a subset of Leon aesthetic V2. It excludes the low resolution images that are smaller than 512 pixels. So including all the subset, it has collected a 2.8 M million. Image text space are selected as source images. So once these images are collected, what they're going to do is they're just doing a visual condition extractor that we're going to apply the each category condition, each conditional task, they're going to apply the extractors. Let's say that it comes up with Kenny, HED, and it goes till the outpainting as well. So the next here, this image says that it is taking each condition task and how it's gonna output for the control net and the UniControl. If you see this Kenny edge, this is something we got generated for the UniControl, and this is for the control net. I feel the UniControl is something it's clear and it's matching the entire prompt. It says the hotel room scene, efficiency, then Q&A bed and sofa, table, desk, TV in brown tone too. So here you can see there's a mismatch in the entire theme we are mentioning is a brown in the control net. But when you see the other HCD2 image and all other conditional tasks, I feel UniControl has a more better visual visibility than compared to other models. So then here comes the UniControl zero shot results. Here it's kind of, we are going to give each condition to this model. Let's say that here you can see a zero shot task, which is a image colorization. As I mentioned earlier, this comes under certain weights that are assigned to the image colorization. In this case, we have done a manual alignment or assignment to the entire weights. So it comes up with depth assignment of 0.6 and segmentation of 0.3 and Kenny of 0.1 for colorization. So this entire slide covers of how a UniControl zero shot tasks are controlled. And then this is a quantitative evaluation that has done for the entire two models, which is a control net and this the UniNet. So here we can see it's visible that which is ours is like UniControl and the control net. It's kind of a tie condition that came up there. So this is visible that control net is not that efficient compared to the UniNet. So UniControl is something like it has an ability to control complex geometric interpretations, and it outperforms the baseline, highlighting the method robustness and capacity to generalize. So coming to the conclusion, the UniControl is a novel unified model for incorporating a wide range of conditions into the generation process of diffusion model. Then the UniControl is something it is designed to be adaptable to various tasks to the employment of two key components, which is MOE style adapter and the task aware hypernet. Next comes the experiment results. This paper has covered a huge range of experiment results that showcase the model robust performance and adaptability across different tasks and conditions, demonstrating its potential for handling complex text to image generation tasks. Yeah, thank you.